I'm Esther Mullins, and I am a postdoctoral research associate with the South Central Climate Science Center and the Southern Plains Transportation Center, based at the University of Oklahoma. Today, I'm going to give you a general introduction to simulating Earth's climate system using global and regional modeling. You can find more detailed discussions of these concepts in other modules on our site. Imagine you're a city planner who is responsible for your town's multi-million-dollar stormwater drainage infrastructure. As you plan, you may be interested to know if and how precipitation may change in your town over the next few decades. We know that our climate is changing, so we cannot assume that the climate variability experienced in our town's past will be the same in the future. As a city planner, you will need some more information, and for that you turn to computer-based models that represent our Earth system. Most of us are familiar with weather forecast models that are shown during the weather portion of our local TV news. These models are based on mathematical equations that describe the physical processes that occur within the land, ocean, and atmosphere. These equations must account for solar and terrestrial radiation, the basic composition and structure of the land, oceans, and atmosphere, and exchanges of energy, momentum, and moisture between the surface and different layers of the atmosphere. Many of these processes occur on scales too small to be computed by the model. In these cases, we can use mathematical approximations that are based on statistical relationships usually found from observational experiments. A weather forecast model runs after forcing it with a set of observations, or initial conditions. These observations include air temperature, moisture, and winds at various heights, location of cloud and precipitation, radiational forcing, such as energy from the sun for that day and time of day, and other known variables. The model then uses the mathematical equations to predict specific weather conditions over the next several days. Climate models also use physical processes in mathematics to calculate how land, oceans, and atmosphere change over longer periods of time, say from years to even centuries. However, because of longer time periods, they must account for other processes. On these timescales, the seasonal, annual, and regional variations of the land surface, snow and ice, ocean circulations, and biosphere must be calculated. These systems interact with our atmosphere to regulate our Earth's climate. To produce a good climate projection, we must also account for changes in Earth's energy budget, which itself is affected by changing greenhouse gas concentrations. The climate models include both natural and human-induced changes in the energy budget over time, or boundary conditions, to make their long-term projections. It is important to know that although the two model types are similar, a climate model and a weather model cannot be directly compared. Sometimes you will hear that climate models cannot possibly be reliable if we can't even predict the weather out more than a couple of weeks. But we just learned that the goals and requirements of these two types of models are different. Climate models compute or project statistical trends and variability in our regional climate over long time periods and are based on changing boundary conditions. Weather models use observations as initial conditions to predict or forecast the weather at a specific time and location. So don't expect a climate model to tell you the weather on your 85th birthday. Because long-term changes in the land, ocean, or ice in one part of the world will cause changes in the atmosphere in other parts of the world, we always begin our climate projections by using a global climate model, or GCM. These models solve multiple equations at every point on a three-dimensional grid across the entire Earth. The more grid points we have, the longer it takes for a computer to crunch the numbers. Even though we use some of the largest supercomputers in the world, there is still not enough computing power to have grid points every kilometer, or what we call high resolution. Instead, a typical horizontal grid spacing might be about 150 to 200 kilometers, or what we call a low resolution grid. This means that there is only one grid point every 150 to 200 kilometers. Clearly, you as a city planner will struggle to apply the information you get from a global climate model because your town might be located between two grid points. Thankfully, there are methods to generate high-resolution regional projections to help city planners and other decision makers. One method is to combine the output of a global climate model with a regional climate model. Regional simply means that we are doing all of those mathematical computations within a specific geographic region or domain, rather than on the whole globe. With a smaller area, we can now use the computing power on grid points that are closer together, or at a higher spatial resolution than our global model. We also can decrease the time step of the model calculations to get higher temporal resolution. The regional climate model uses the output and boundary conditions from a global climate model as its input. The regional model then is tied to or forced by the large-scale changes in the global model, but simulates future climate on a finer grid, say 5 to 50 kilometers. The regional model is able to resolve physical processes that the global model cannot see because of its large grid box sizes. For example, the regional model can now resolve some of the significant precipitation and temperature gradients produced in mountainous or coastal regions. At resolutions around 4 kilometers or less, these regional models can even resolve complexes of thunderstorms that bring heavy precipitation to many regions of the world. Unfortunately, the computational cost of regional models is very large, so few researchers can use them routinely. Because these regional models compute the dynamics of the atmosphere and scale to a finer grid, we refer to this climate projection process as dynamical downscaling. Fortunately, there is another way to project regional climate changes that is much less computationally intensive. This method is called statistical downscaling. It uses statistical relationships between historical observations and the output of the global climate model to estimate future climate changes in a specified region on a fine resolution grid, sometimes on the order of 5 to 10 kilometers. Although this approach also resolves fine-scale behavior and does not require supercomputers, it is only effective for regions with a good long-term observations and a solid statistical relationship between the model output and the observations. These two regional approaches provide climate change projections at the scales that you as a city planner can use to make decisions. For example, you may find that your region is projected to have an increase in the frequency of intense precipitation events in the next several decades. You may need to build new infrastructure or adapt existing infrastructure to mitigate potential flooding. Even with detailed regional climate projections, there are also limitations and uncertainties associated with them that you need to understand. The remaining videos in this series will discuss details of these limitations and uncertainties. Thank you.